Yeah. So last time, the method we used here, we call it binary exponentiation. Binary exponentiation. Yeah. Here you can see when n is the power of 2, you calculate this. It's very easy. Power of 2, very easy. So you just keep doing the square operation. Yeah. But here, when n is not the power of 2, so you need to, consider many relatively complicated situations. Here, we want to simplify that situation. Simplify that situation. Yeah. So here, there is a way. So if you look at the expression here, this expression related to the binary representation of n. So but you can write 217 as a binary number, right? Yeah. So these numbers corresponds to binary representation. So if I show you, because this corresponds to 2 to the 7th, okay? Yeah. 2 to the 6th, 2 to the 4th, 2 to the 3rd, 2 to the 0, okay? Yeah. So let's look at the binary representation. Yeah. Position 0, 1, 2, 3, 4, 5, 6, 7. Okay? So the position number. So let me, put it here. Okay? All right. So here at the 0 position you have 1, right? So I put a 1 here. 8, it appears at a position 3. Yeah, because the exponent number is 3. So the 0 position, 1 position should be 0, because no term corresponds to position 1. No term corresponds to position 2, right? So I put a 0. And you have 1 term at the position 3, so we put a 1 at position 3. Position 4, 1, right? Yeah. Position 5, nothing, so 0. Position 6, 1. Position 7, 1. Yeah, see? 0, 1, 0, 1 in this way, from most significant bit to least significant bit, and parenthesis, because binary system. So our representation is this way. Okay, parentheses are around this, bits, sequence of bits, and system number, binary, not 2. Yeah. Yeah. So here you can see this decomposition directly related to the binary representation of the given integer n. Yeah. Yeah. Yeah.
So
question?
The question
Yeah.
is about from last class. So you got down there, I think you asked a question at the end of class.
Uh-huh.
How many data values, something?
Multiplications,
Yeah,
right?
multiplications, and you got 11 there, right?
Yeah, 11.
I get the 4, you multiply them together with 7. I understand how you get 7.
Yeah.
But 7, which is equate to 128, right? X to 128
Yeah.
is 7.
Right.
What about the remaining? So 64, 16, so obviously...
Remaining, when you get this one,
Yeah.
you go through all of them.
So
You already covered. Yeah.
Oh,
You cover it. Right? You don't waste it, right? Yeah. Yeah. Because how do you get this last term? You go through the sequence one by one.
so no matter how high that is, we're just going to take whatever we use to get the highest.
Yes, yes, yes. Yeah. Yeah. Because you need to calculate the last one anyway, right? Yeah. So you do not waste it. When you do the intermediate calculation, you do not waste intermediate calculation. Yeah. So keep the resource. That's our resource. Okay? Yeah? So we treat this part the resource pool. We maintain a resource pool. Okay? Yeah. All right, yeah. So this idea. Try to, after we learn, although this is a simple example, but in your future, in your mind, you should have this idea. When you can reuse the resource, you can save your computation operations. Operations. Yeah. Improve your efficiency. Yeah. All right, so let's continue. All right. Yeah, so here, right, so that's some people, because given integer n here, people can easily convert it to the binary representation, right? Yeah. But here, when you write the program, you have better way to do it. Yeah. Although you can, using this way to do it, but that's not the best way. Yeah. So the best way, the next slide, I give you the best way. Yeah. The pseudocode, you can understand the idea easily. This function, we write a pseudocode, repeat square root. Yeah. So we use the recursion here. When we use recursion, then we can make it very simple. Recursion, right? Recursion, that's the topic of our module 3. So in module 3, we will use the whole module to cover the recursion topic. Very important. Yeah. Here, but we need to use it. Okay, recursion. All right, so when we start, we check some, the simplest two cases, n equals 0, n equals 1. Yeah. Two base cases. Base cases, we can return the result immediately. Yeah. So n equals 0, return 1. Yeah. First base case. Second base case, n equals 1, we return x. Okay? All right. After that, we assume n greater or equal to 2. N is an integer, at least 2, value 2. All right. Then we will do the square root operation. Divided by 2. N divided by 2. So that's the else part. That's the main processing part. Okay? Yeah. All right. Main processing part here. Look at this line. This line is very important. So recursive function call. Okay? This function we calls itself repeated squaring, but we call it parameter, same x parameter, but the n, we do integer division. N divided by 2, integer division. Okay? N integer division. Yeah. We can do it, right? No fractional part, right? Yeah, because integer division, it must be an integer. Okay? The remainder truncated. Yeah, we only keep the integer part. N divided by 2. All right. So we call this function, we expect a value to be returned. We store it in this product variable. Okay? Yeah, because we need to use it. Yeah. So it's a temporary variable. We store this value. All right. Next, we calculate square of this product. Prod times prod square, right? Square of this temporary variable, store it in the result. Okay? Yeah, it's a square. All right? Now, let's think about, is this result variable contains the final result of this function or not? We need to think about this. Yeah, not quite. Okay? Sometimes it contains the final result. Sometimes it does not contain the final result. Depends on n is even or odd. Look at, if n is even, n over 2, half of that integer, no remainder, right? Then this result, product square, that's the final result, right? Yeah. Nothing we missed. Yeah. Nothing missed. Yeah. But when n is odd number, then it's not a final result, right? Yeah. Yeah. Because, but although it's not a final result, what's the difference between this value and the final result? Can you see it? No, it's not final result. Slightly short, a little short. But what's that little gap? There is a little gap between this value and the final result. So we need to bring it back. Okay? All right. We check even or odd. When n mod 2 equals 1, that means n is odd, right? Odd number. Mod, the percent sign modular operation. N mod 2, remainder is 1. Yeah, because you get the remainder. Remainder equals 1. It's an odd number. If it's an odd number, your final result should be this value times another x, right? Yeah, because here, when you do division by 2, you truncate that remainder part, right? Yeah, remainder part is truncated. Now you bring that truncated x back. Yeah. So you need to update your result value by another multiplication. X multiplies the previous result value. Now, bring that truncated part back. Okay? Yeah. Try to, in your mind, try to follow that logic. Yeah. So all these, so we follow the logic. Yeah. All right. That's the odd case. For even case, we don't need to update result, right? For the even, this is the correct one. We do nothing. We don't need to do anything. For the odd case, we treat these two lines as the correction part, because the current result number is incorrect. We want to correct it. Yeah? So we use these two lines to correct that result number. Now we are ready to return the final result. Return final result. Pretty neat. Yeah. Using recursion, you can see, if you do not use this recursion, you can imagine how complicated your implementation. Because even you use the binary representation, then you need to use the for loop. Yeah, you can do it. Yeah, but pretty complicated. Yeah, but here, recursion. Yeah. So this example, you can see the power of recursion. Yeah. So in our module 3, we will learn how to use the power of recursion. Yeah, the first view. Yeah. All right. Yeah. So in your implementation, you use this way. Okay. So all three algorithms given. Yeah. So you just write carefully. Yeah, but the first time after you complete implementation of 3 algorithms, when you do the first testing, it's very likely you may not get the same result for all 3 functions. Yeah. It's highly likely. You need to fix, because several little places you may miss something. Yeah. You may miss something. Okay? Yeah. So that's why I ask you to compare, do experiments on small input. Yeah. So you can quickly see your 3 results may not be the same. So you need to fix your code. Yeah. All right, we finished this topic. Let's move to the next topic. This time we consider a special case. How special? Because when you apply the Horner's rule, so this special is non-monomial, okay? Yeah. So we pass that monomial thing. Yeah. For the general, when you apply Horner's rule, always for the general case. Yeah. Special case, Horner's rule may not be the best solution. Yeah. The general case, it is the best solution. Yeah. All right, but here, I'd like to give you some interesting special case here. Yeah. That is Pascal's triangle. Okay? So let me give you this, interesting mathematical structure. Yeah. So you may heard of, some of you may hear of it. Yeah. Yeah. So that is, so in your discrete math, you have the formula. Discrete math, you have a formula, okay? Yeah. So this triangle, lists the coefficients of binomials. So monomial, now we go to binomial, okay? Polynomial, monomial, binomial, all right? Yeah. So what's that binomial? Binomial formula. X plus y parenthesis to the n. That's the binomial. Inside parenthesis, two terms. Okay. Yeah. But raised to the nth power. Yeah. And there is a formula, binomial formula for this expression. Yeah. So you expand this binomial. Yeah. Then you get the coefficients. All these combinatorial numbers, coefficients represented in combinatorial numbers. Yeah. So what's the definition of the combinatorial numbers? Yeah. Here, definition is n factorial over k factorial times n minus k factorial. Okay? Yeah. So that's the definition of this combinatorial number. Okay? Yeah. So we call this, we need to read, right? Yeah. N choose 0. Okay? N. Yeah. In n objects, we choose the bottom number of it. Okay. N choose 1. Okay? N choose 2. N choose k. N choose k. Okay? Yeah. Yeah. So given n balls, you need to pick k of them. How many ways to pick k different k balls from n balls? Yeah. So the answer is this answer. Okay? Yeah. Formula, yeah. Special expression like that. Okay? But not a combinatorial number. Yeah. All right. This formula is also called a Newton's formula. Okay? Yeah. Newton discovered this formula. Newton's formula. Okay? All right. But when you put a specific n number there, then when n equals 0, that's 1. Okay? When n, yeah, so let me list it here. N equals 0, because you only have 1 there. Okay? But n equals 1, you have coefficient 1, 1. 1 for x, 1 for y, so 1, 1. When n equals 2, you have 1, 2, 1. If you write the expansion of this binomial, you get a 1, 2, 1, and so on. Cube 1, 3, 3, 1. Fourth, this row, coefficients. Then, and so on. Okay? To the bottom. Yeah. And so Pascal, a mathematician, discovered this triangle structure. There is a property. Okay? All right. Here you can see this 2 equals sum of 1 and 1. Sum of the two two efficient, two numbers above this line on its shoulder. Okay? Yeah. Yeah. So you can see 3 equals 1 plus 2. 3, 1 plus 2, and so on. Always like that. Okay? Yeah. Yeah. All the way down. Okay? Yeah. That property. Yeah. Yeah. Always. 20 equals 10 plus 10. Yeah. Always satisfies that property. 35 equals 15 plus 20. Okay? Yeah. So that's the, well-known Pascal's triangle. All right. Now, with this special structure here, I want to talk about special polynomial. When we evaluate special polynomial, we may take advantage of the special structure. Do not waste it. No. No. All right, let me show you one example here. How many multiplications do we need to calculate this polynomial? See? Here, I give you a special polynomial. Not general polynomial. Okay? It's a special polynomial. And its coefficient has a special pattern. Here, we need to take advantage of the special pattern. Okay? Yeah. 1, 5, 10, 10, 5, 1. Look at this line. 1, 5, 10, 10, 5, 1. It corresponds to one row in this Pascal's triangle. Okay? It happens to be one of the rows in the Pascal's triangle. What's the conclusion? After you see it, how do you connect? When you find this property, any conclusion you can get? Okay. Yeah. Can we write this polynomial as, because if you apply Horner's rule, then it's not the best. Tell me, if you apply Horner's rule, how many multiplications do you need? Horner's rule. How many multiplications? The general case, Horner's rule. Look at the degree number. Horner's rule, degree number. Degree 5. 5, I heard 5, but let me remind you, the first reaction is 5, but pay attention to the coefficient 1 as the leading coefficient. 1. 1 is the leading, that means the last multiplication you can save it, right? Our last multiplication is leading coefficient times x. Now you don't need that, right? So the answer is 4, not 5. Because you do not need to do the last multiplication. Okay? Yeah. So the best you can do is by Horner's rule, 4 multiplications. All right. But now we want to take advantage of the special structure. All right. All right. Based on Pascal's triangle structure, can we write the same polynomial as x plus 1 parenthesis to the 5th? Newton's formula, binomial formula. Can we write in that way? Okay? Yeah? Right? Yeah? The formula, right? When we write in that way, this new structure, can we use fewer number of multiplications to find the value? Fewer. Say a few multiplications. Is it possible? Right? Yeah. Because here, addition, we do not count addition. Okay? Attention, extremely fast, comparing with multiplication. 10-to-1 ratio. So we never worry about the addition. Okay? Yeah, we never worry about the addition. Yeah. We only count the number of multiplications. Yeah, let me show you how to do it. First multiplication, x plus 1 times x plus 1 multiplication. Get a square. Repeat the squaring, right? Second multiplication, we need to do the, square operation. Yeah. 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 Because we have this value. We just copy those two values. One multiplication, we can get a x plus 1 parenthesis to the 4th. That's our second multiplication. Then the last multiplication, parenthesis to the 4th times x plus 1 parenthesis. Last multiplication. So we need 3 multiplications, not a 4. We can say 1, right? Say 3 multiplications instead of 4. We improve it. Okay? Yeah. Better than Horner's rule. Yeah. Yeah. So from this example, you can see how to take advantage of the special structure. No. Okay? No? No. Yeah. So this special case. Yeah. So you will get a similar question in quiz, in your first quiz. Okay? Yeah. In the end of this week, this weekend, you will get a quiz number 1, first quiz. Yeah. Covering whole module 1. Yeah. We will finish module 1 this week. Yeah. So do a quiz, but it's a 1-week quiz. Okay, so it's not a so you need to complete it quickly. Yeah. Yeah. So you have 1 week of time, study and work on question, because no time limit on the quiz. No time limit. Yeah. You can, study for a while, then work a few questions, then study. Just make sure you submit it by the deadline. Yeah. All right. Yeah. So we finished part B. Yeah. Next, I need to move to part C. Yeah. All right. Part C, a new topic. Role of data structures in algorithm. Yeah. Oops, sorry. C.1, search unordered arrays. Yeah. All right. First, let me give you the question. Our problem number 3 for this class. Search an unordered array. Yeah. It's a very simple question, but we need to learn some basic concepts. Yeah. Given an unordered array, that's our data, our input data, unordered array. Representation, capital A. Yeah. With indices from 0 through n minus 1. And a search key K. The search key, this key must be given. The question, find an index I such that K equals A of I. Yeah, so that's the question. Simple search problem, computing problem. And this topic, I'll give you, so the problem type here, the basic problem type, it's a search type. For this class, we will learn 3 basic problem type. First one, search. Second one's sort. Third one, selection. Yeah, 3 basic type. All right. Here, the data structure we use in this question, simple array. Array, it's a simple data structure. Yeah. Okay. All right. And the reference, section 2.1. All right. Yeah. Part B, I jump to section 6.5 because the reason I need to do a programming project. Okay. But after that, I will follow the natural order of the textbook. Okay? Yeah. So do not jump too much. Okay? Yeah. So based on the sequence. All right. Yeah. Oh, one student asked me to list all the reference chapter sections for each module. Yeah, so I will do that. Yeah, yeah. So because last semester, some student mentioned that. Yeah, asking. Yeah, but I will do that. So later I just post that information. Yeah. All right. Question: why the data structures are important in algorithm design? Yeah, this basic question. Data structure. Why is so important? In our first class, we talk about that question. In our first class, when we work on the chessboard question, yeah, we learned the idea data organization is very important, right? To organize the data, that's very, so the data structure is used to organize your data. That's the role, the main role. Okay. All right. Oh, sorry. Going back. Yeah. Now, through data structures, we can make our data well organized. When you need to find your data, you can do in a fast way. Yeah. You can do it in a fast way. For example, here, we store the data in an unordered array. Think about it. If we can make this data ordered, make data ordered, that's a data organizing step, right? Yeah. You order your data, so we organize our data. After that, can you find your data faster? When the data is organized, yeah, because you make it ordered. Okay? How do you make it ordered? Sorting. Yeah. Next, we will learn sorting. Several sorting algorithms. So we can make it ordered. Okay? After we make it ordered, because there is a good structure in your data. We build a good structure in your data. Then we can apply binary search to find the data faster, right? Yeah, because after you arrange your data ordered, you can apply binary search. If unordered, you cannot apply binary search. That's slower. Yeah. So here we do the search on unordered array. So we can only use this topic, we call it sequential search or linear search. Yeah. Linear search. Yeah. All right. Yeah. All right. So, yeah. So the benefit you can see easily. Yeah. But here we do not plan to order it. Yeah. So we just find a solution directly. Basic operation here, comparison. Yeah. We need to compare each element in the array with the given key and check if they are the same. Yeah. All right. And when we do comparison, we need to look at the cases. Yeah. When we do comparison, we start from the first element, I equals 0. First element, we compare k with the first element. Okay. Then, if k equals A of I, that's the current element, yeah, because this I index value is incremental, yeah, every time it's by 1. Yeah. If K equals the current element, the value of the current element, then we find it, right? Yeah. Another case, K not equal to the current element. Greater, less, but unequal. Yeah. Not equal. Yeah, so these 2 cases. Now we do not need to consider 3 cases. Okay? Yeah. 1 greater, 1 less than, unnecessary. Yeah. 1 more case. Yeah. So we combine greater than, less than in 1 case, unequal case. Yeah. So for the equal case, return I. When you're done, you complete your algorithm. Yeah. But not equal, then you need to do the next iteration. Keep doing iterations. Yeah. All right? Yeah. And when you do the following iterations, yeah, sooner or later you will reach the last array element, right? Yeah. Yeah. So when your I equals n minus 1, you compare key K with the last element and still unequal, not equal, so you return -1 as the value. Yeah. Because -1 cannot be any index number, right? Index number cannot be -1. So -1 will tell people a special meaning. That means the given key cannot be found in the given array. Yeah. Yeah. If it can be found, you return the index value, I. Yeah. So valid index number, I. Yeah. So people know where to find it. Yeah. But if no match, there is no match in the given array, you need to send some signal, some information. Yeah. So this special value to tell people it does not exist. Yeah. All right, so that's the basic algorithm here. Yeah. All right. Yeah. So this algorithm we call a sequential search or linear search. Yeah. 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 Same meaning. Yeah. All right. Next, we need to do analysis on this algorithm. Yeah. Although very simple, yeah, but we can learn some basic concepts. Yeah. All right. Next, I want to do analysis. To do count. Yeah. Remember in our early lectures, we want some objective, stable measure for efficiency, right? Here. Yeah. So the objective, stable measure will count the number of comparisons. That's stable, right? Yeah. 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 Number of comparisons. Yeah. All right. Here, let's count. Yeah. When we count the number of comparisons, we need to cover all the possible cases. There, we need to exhaust all the cases in this problem. Yeah. So what are all the cases? Yeah. Can you see we list all the possible cases? Yeah. The first case, capital K equals the first element, second element, and so on. The last one, no match case. So we cover all the possible cases here. Yeah. Let's do the counting. Yeah. The first case, yeah, very easy. one comparison is enough, right? After the first comparison, you can say if K equals first element or not. Second case, two comparisons is enough, right? After two comparisons, you can tell if K equals that element or not, and so on. 3, 4, and so on, okay? Yeah. So this one, and, but at the end, there is a no match case. Yeah. How many comparisons do you need for that no match case? And, still and. Because you just compare given key to all the elements, right? You have n elements. The total number of elements, that's n. You do not need to do more than that. So after n comparisons, you can say if there is a match or not. Yeah, right? Yeah. That's all the cases, right? Yeah. You do not miss anyone here. So you cover all the cases, n plus 1 cases. N plus 1 cases. All right. Our next step, we need to make our conclusion. After you list all these n plus 1 cases, you need to make conclusion. Telling people, how fast is your algorithm? Okay? Yeah. But when we tell people, we have several cases to explain the efficiency. The first one is the best case of this algorithm. Best case. So that's the first one. One comparison. We call it best case efficiency. Okay? All right. Then the last two cases, the largest number of comparisons we need to use for the last two cases, so we call it a worst case. Yeah, worst case efficiency. Yeah. So these two concepts. Best case efficiency, worst case efficiency, two concepts. Yeah. But if people ask you, what is the overall efficiency? Overall efficiency. Then the best case is not good. Yeah. The worst case also not good. Yeah. So what is the best overall case? The best way to give a fair measure for the overall efficiency. Yeah. So we need to learn that concept. Yeah. The most important concept of this part C is this one. So that is not best case, not the worst case. That is because to give the overall efficiency description, you need to, your measure should cover all the cases here. Okay? The best case only cover the best case. The worst case cover the worst case, but not all the cases, right? Other cases, they do not cover. But here, your overall efficiency measure, you should cover, include all the cases. Well, that's fair way, right? That's the fair way. But the question is how to include. Yeah. So you want to include. But when you include them, how to combine all the cases? That's another question. What is the best way to combine all the cases? That's the most important question here. Okay, all right. Yeah. So here, so we already list all the cases. Yeah. So this question, for this particular problem, that's easy. But later, when we learn other relatively complicated computing problems, that may not be easy. Yeah. List all the cases, that may not be easy. For example, sorting. when we solve an n-element array, how do you list all the possible cases? Right? Extremely hard. Yeah, extremely hard. Yeah. Although it's possible, yeah, but it's hard. Yeah. Yeah, but here it's very easy. Yeah. All right. The next question: how to combine all the cases? What is the best way to combine all the cases? What is some fair way? Maybe some fair way to combine all the cases. Yeah, think about that question. Okay? Yeah. All right. Yeah. Here, before we do that, yeah, so we have to combine all the cases. But before we do that, we need to make appropriate assumptions. Assumptions. Yeah. All right. Yeah. When we make assumptions, we need to make sure it's fair assumption. Okay? Yeah. So, reflect to the real world situation. Yeah. All right. C.2, let's talk about average efficiency. Let's answer that question. Yeah. The most important question of part C. Yeah. All right. Analysis. Yeah. So now we need to, find that fair way. Yeah. But we need to make some assumptions before we do that. All right. Yeah. Our data. So our current data. Okay. All right. Then we make assumptions. Yeah. Reasonable assumptions. Yeah. All right. Assume that all these base cases have the same probability. See, the first n cases, yeah, we do not look at the no match case. Okay, yeah, so, curly braces, here, bottom, yeah, and we assume the probability. Yeah, the case one, each of these n cases occurs with the same probability. Is it reasonable? Yeah. That's reasonable. Yeah. That's our first assumption. Very reasonable. All right. Second assumption. Now we need to consider that no match case. Yeah? Because here it's not reasonable. We assume the no match case occurs with the same probability as any of the previous cases. That's not reasonable. You cannot say that. You cannot say that. So we have to use another assumption for the last special case. Yeah. We need to consider the probability for no match case. Yeah? Because the -1 case, the return value, yeah? If your function returns the index number, valid index number, that's the first n cases. If your function returns the -1 number, all right, that's the no match case. Okay? So you separate these two cases. Then this time you make your assumption, second assumption. The probability for the index case is P. P. Yeah. P some number should be given. Okay? Yeah. If P is unknown, then you cannot find the answer. P must be known, but how to know P? Yeah. So I will talk about next. Yeah. All right. The probability number must be between 0 and 1. Yeah. Probability concept and the basic properties, yeah, you can see from the discrete math, right? Yeah, discrete math. All right, the probability. Then this one, that's the complementary part, all right? Yeah. Other than this P, the complementary part, so its probability is 1 minus P. No match case, 1 minus P. All right? Yeah. So with these two assumptions, now we are ready to calculate that overall efficiency in a fair way. Yeah. This time, with these numbers, yeah, we can do the last round calculation. Yeah. All right. Yeah. How to, yeah, let me explain before I do that calculation. How to get the little p probability value. Yeah. So usually people do it in this way. Do statistics based on the history data. Yeah. History data. Because you need to apply this algorithm, you know, many times in the real world applications. So you can collect history data. Okay, do statistics. Yeah. Yeah. Then you can get an estimated p number. Yeah. So in your calculation, you can use that p number. Okay, all right. Yeah. Or we can do dynamic statistics. Yeah, because when you run your algorithm the first time, second time, third time, 100 times, 1,000 times, you just do statistics dynamically. Yeah. Every time you collect a new data point, then you update your formula for the p-value. Yeah. So that's another way people can do it. All right. Now, we assume we have that p. Okay? Yeah. So we have it. Yeah. Now, the last formula, we need to calculate that. Question? Yeah. Oh, all right. Yeah. All right. Yeah. Last question. Our final step. Yeah. Final step, the most important one. All right. Yeah. Remember, we need to do some fair combination way, right? Yeah, combine all the cases in a, fair way, yeah, best way. Yeah. All right. First subcase, yeah. So let's treat this index case as the first subcase. Yeah. 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 All the first n cases. Yeah. The first subcase, and the second subcase, this no match case. Second subcase. So we have two subcases. Okay. All right. Let's calculate what is, yeah. For the first subcase, if I ask you to use one number to give the best description for the first subcase, how do you do it? One number. First subcase, there are all these n cases. But you cannot use these n numbers altogether, right? Yeah. So you can only give me one number, but that one number should cover all these n cases in a fair way. That's the average number. Average, yeah. When you take average, that's a fair way, right? Average of n numbers. How fair it is. Okay? Yeah? So that you take the average of the first n numbers. Okay? After simplification, 1/2 of n plus 1. Okay? 1/2 of n plus 1. Yeah? 1 plus n, the smallest number, the largest number, adding together, divided by 2, that is the average. See? Yeah. From the formula, we get the same number. Yeah. Right? That's the average case efficiency for the first subcase. But we also want to have the average case efficiency for the second subcase. What's that number? Second subcase. we need some number to represent second subcase. And it should be an average number, right? Yeah. What do you feel the average number should be? N. Because you only have one case. The average of one number is the same number, right? Because here you only have one number. When you take an average on one number, you get the same number, right? Okay, yeah. So that simple concept. All right, now you have two numbers. First subcase, this number. Second subcase, that number. The next question, how to combine these two numbers to get a final overall efficiency number. Another combination between these two numbers in a fair way. That's the final step we need to do. All right. For the first subcase, the probability is P. This time we need to use the probability number. Yeah? How to use the probability number? Yeah. This last step, we need to use the probability number. The first subcase, its corresponding probability is P. The second subcase, its corresponding probability number is 1 minus P. Combine these two cases with their corresponding probability numbers. How to do it? Yeah. Here, you need to have some basic understanding of the probability concept. Okay? Yeah. Not very deep, just basic understanding of the probability concept. Okay? The percentage, right? Yeah? Yeah. Yeah. The percentage of the occurrence of the first subcase or the second subcase. Yeah. The larger the probability, then more contribution, the larger the P, more contribution from the first subcase, right? Yeah. The smaller the P, then more contribution from the second subcase, right? Yeah. Yeah. That's the straightforward understanding. So with this understanding, now when you put them together, okay? Put them together, but when you put them together, you need to associate these two probability numbers with the average case efficiency of these two subcases. You need to associate. Yeah, because the phenomenon we just observed should be considered, should be covered in your final formula. Okay? Yeah. So now let me write the final formula. The final formula, we have a name for it. We call it weighted average. It is the average. But what average? We do weighted average. Yeah. So this name here is important. Weighted average. How to allocate the weights. Choose appropriate weights for each subcase. The first subcase, second subcase, their corresponding probability numbers are used as the weights when we do the weighted average. That's the understanding of our average meaning here. How do you do the average? We do the weighted average. What are the weights? Their corresponding probabilities. That's the weights. All right, yeah. So this is your final formula for the average case efficiency for this problem. Average case efficiency, we call it. And this measure is the best for the overall efficiency. The best one for the overall efficiency. If people ask overall efficiency, then you should provide this number. Okay? Yeah. All right. But here, yeah, just before we finish the class, yeah, because we need to prepare for Module 2, yeah, our Module 2. So here I want to introduce a dominant term. Yeah. So in this function, you can see, yeah, this function, n is the variable. Yeah. N number keeps changing. Yeah. But a p is a fixed number, fixed constant. Yeah. P does not change. Yeah. P, as soon as you get the statistic data, so you fix it. But n can change. Yeah. Then, if you consider the total value of this function, yeah. So there is a concept called a dominant term. Dominant term, yeah. Because here, this function, can we treat it as a polynomial? Yeah. It is a polynomial, right? Yeah. It is a polynomial. When you have a polynomial, you have a term with the highest degree, right? Highest degree term. Okay? Yeah. In a polynomial, you have one term with the highest degree. Yeah. So that term increases the fastest, right? Yeah. Increases the fastest. Yeah. So that term we call a dominant term. Yeah. All right. So in this formula, what is the dominant term? Okay? Yeah. All right. So in this one, the dominant term, we can calculate. Yeah? Because this, when we calculate the term, we use the variable n. Yeah. P constant, so we treat it as coefficient part. Yeah? And you can see the term with the highest degree number is this term. Yeah. This term. So we call it the dominant term. Yeah. This concept is useful. This concept is useful in our Module 2 when we talk about approximation. Yeah. Because we need to look at the approximation of the efficiency function. So we need to use this concept. Yeah. All right, yeah, let me stop right here. So we finish part C. Yeah. Next time, we will do part D, the last part of Module 1. Yeah. Then we finish the whole Module 1.